Now that we have those established limits, we're going to move on and look at first principles. So this is a section of the sine graph. So I'm going to take a general point here, x sine x, and a point up here, x plus h, and this will then be the sine of x plus h. And we're going to take the chord between these 2 points, and in the usual way we'll work out the gradient of that chord. So delta y over delta x, that's the difference in y over the difference in x, is f of x plus h minus f of x over h. And in this case that's the sine of x plus h, take away sine x over h. Now remember from year 11 that sine of x plus h is sine x cos h plus cos x sine h, and then we've got the minus sine x on the end here and divide by h. So all I've done here is just rearrange this slightly. I've brought the sine x, the minus sine x here into the middle, so there's nothing too technical about what I've done in that line. But it does mean with these first 2 terms that I can take out the common factor of sine x. So I now have sine x into cos h plus, minus 1, and then we've got the cos x sine h on the end, and we're dividing by h. And then we can split this fraction because it's over this denominator, like so. So this term here over h plus this term here over h. dy dx is the limit as h tends to 0 of this expression. So what we're doing here, this is a limit of a sum, and we're saying that that's equal to the sum of the 2 individual limits. You can see how we split that. Once again, you're just going to have to accept that. X is not involved in this limiting process at all. So the sine x can come out of this one, and the cos x can come out of this one. There's nothing too technical about that. It's just it's h tending to 0, and h is not involved in this sine x, h is not involved in this cos x, so they can come out. Using the limits we investigated before, remember this one is going to tend to 1, and this one is going to tend to 0, we get dy dx is just equal to cos x. In a similar way, it can be shown that y is equal to cos x tends to dy dx is equal to negative sine x. So if y is cos x, the differential is negative sine x. And we can show that with exactly the same limits and in exactly the same sort of way. There's a cyclic pattern to trigonometric differentiation as shown in the diagram below. So sine x differentiates to cos x. We established that. From here, cos x differentiates to negative sine x. Since sine x differentiates to cos x, negative sine x must differentiate to negative cos x. And since cos x goes to negative sine x, negative cos x must go round to sine x. So this is what happens when we differentiate. Now since integration is the reverse process, this is just for future reference, the diagram just goes around in the opposite direction. So the red stuff here is what happens when we integrate. I always just remember this diagram. It's a really handy way of seeing what happens when we're doing trigonometric calculus.